Yes, okay. Yeah, so I'm just going to walk you through the rationale for the suggestion that we've made in our paper. And as we said before, it's Plasma Power, Our Renewable Advantage. And my co-authors are in the room here, Tony Murphy and Yunjia from CSIRO, both of them, one from Melbourne and one from Sydney. Okay, so let's start from something that really excites me. We're finally moving ahead with renewables, and in a big way. So this is just one project that has been started in Australia, and it's actually very ambitious. I'm thrilled to be involved in it in a research capacity as well. We have a linkage grant with these people. It's Sun Cable. They're planning to build the world's biggest ever solar array in Australia, in a town called Elliott, in our desert. And this highlights that we have a huge advantage in this space because we have a lot of land that we don't use, and we have an incredible solar flux landing on our country. So we actually could be a generator and a major exporter of energy. Now, of course, we also have some mining, so we have a lot of high purity silicon, and we could also be manufacturing a lot of these things. So I'm going to be showing you how this move to renewables, we can actually build on this to bring manufacturing back and actually be value adding to this renewable energy resources that we have. So yeah, as you all know, the political will is finally here for a rapid solar expansion, and that's what we're seeing. And there's a couple of quotes here. Australia has been a world leader in PV research for decades. The same universities that blazed the solar PV trail, which of course UNSW is one of the leaders, world leaders in PV, and unfortunately a lot of that technology went to China, and we're now buying it back. So let's see if we can correct that this time and actually jump in and create and keep and develop some of that technology that we can then export to others. Australia already has the highest per capita solar rooftop in the world, and there are several mega projects, and Sun Cable is one of those in the pipeline. There are more. So this is really exciting, and we are going to have much more energy than we can use if we continue down this trajectory. So what can we do with some of this energy? What is plasma? I guess not all of you know that, so that's where I'm going to go next. So you all know about solids, liquids, gases. As we put in energy, we go from a solid to a liquid to a gas. If you put in more energy at that point, you get a plasma. So plasma is essentially a gas where you've taken off sufficient electrons from the molecules of the gas to get positive and negative charges in the system. And you can manipulate this with electric and magnetic fields, of course, because charges respond to those. So it's a fantastic state of matter. We call it the fourth state of matter, to do a lot of exciting things. Chemistry, we can modify materials, we can make new materials using the plasmas. Now, the exciting thing, why am I going from solar energy to this? Well, it basically is the material that you're trying to modify, the feedstock, and energy in the form of electricity that generates a plasma. So we generate it by applying electric fields. And those electric fields accelerate a few electrons that are always in the atmosphere, and they accelerate them. If they accelerate them to enough to ionize on the collision, you get 2 electrons, and then they collide, 4 electrons, and this is an avalanche, and suddenly you have a plasma. Just electricity to do that. And the other neat thing is there's no heating that you need to do, so you can turn it on immediately. You turn it on and you see the plasma light up immediately. So it can track the variability in solar generation, which we've heard a lot about and is an issue. So there are a number of different types of plasma. I'm not going to go into this in detail, but essentially we have really hot ones, thermal plasmas, where everything's in equilibrium and the molecular species are as hot as the electrons. But we can also make low temperature plasmas where the electrons are really hot, but because they're very light, they don't transfer a lot of energy. So you can see a person actually holding a plasma to their skin. So that, yeah, wide range of these plasmas. Now, we're not the only ones to have noticed this. So a colleague of mine from the University of Sydney, PJ Cullen, and myself were invited to the International Atomic Energy Agency just a month ago. We were there in Vienna at their headquarters, and they told us, we have never worked with plasmas before, but you know what? They contain atoms. That's what we do. So we've invited you guys here because we see an opportunity for this type of tech to couple with renewables. And Europe, of course, is going to renewables in all of the member countries. And they want to set up coordinated research projects in this space where they bring in all the member states to try and accelerate this technology forward. And so they ran this technical meeting on emerging applications in plasma science and technology, looking at applications across the board in health, in manufacturing, in chemical industry, in agriculture. It was a really exciting week-long meeting. Okay, so just to give you a feel for what we have, this is from my own research group that we've been doing in Sydney on plasma. So we've used it in the past to modify surfaces of materials and create biofunctionality for biomedical purposes. It has applications in drug testing without animals, personalised medicine, and ultimately we hope to be able to do enough on these surfaces to create in 3D bioprinting actual organs from patients' own cells, because we can now reprogram cells to grow on other surfaces and to differentiate into the cell types we need. So this technology was awarded the Australian Innovation Challenge Award back in 2011, and it's now being taken forward commercially by a company spun out by a colleague of mine from the medical sciences in Sydney. That company's called Cultron. We also use plasma to make nanoparticles that are able to couple drugs, targeting agents, imaging agents for theranostic type and diagnostic as well as therapeutic applications. So here you can just see that the way that's generated in a plasma in the top schematic there, how we create the nanoparticles. That's an image of actually collecting them and optimizing the process. And then here they are with all the cargo to go into the biomedical applications. And they're fully organic, so they're also non-toxic. And we're branching out into 3D scaffolds as well for biomedicine, where we can expand stem cells for cell therapy. Microfluidics, so again, we use a plasma to treat all of the walls of these tiny microfluidic devices to get cells to grow on them in a very biomimetic way, so that we can create arteries. So we've actually created a mimic of an artery to test cardiovascular drugs in, with a colleague at University of Sydney as well in the biomedical sciences. And then I mentioned, of course, as well, 3D bioprinting. We're using an atmospheric type of plasma, the one you saw held against the person's face, in a 3D bioprinter to functionalise the surfaces of that. Another work that came out of my lab some time ago, and this is just to show you that we have some fantastic students who actually at the end of their PhDs, this was work on using a plasma as a thruster in space. This particular plasma uses a solid as a feedstock and creates from a metal a plasma. And there's a lot of metal up in space, that's space junk. So the idea there is to recycle that as fuel for thrusters in space. And that's Paddy Newman, who did his honours and his PhD with me. He's now spun off this company and he actually is now testing this in space. So it's fantastic. And we have lots of great students that I'd love to see take these trajectories. So what's the idea here? Okay, we have all this renewable energy. It fluctuates, we want to tap it and we want to export it. So we need this new concept, power to X. We're taking that power and we need to convert it into something that we can ship. Now, Sun Cable has the model that they're going to install a huge undersea cable and, transmission wires to Darwin, undersea cable to Singapore and supply 15% of their energy. That's great, but it's an awful lot of undersea cables and it's not that flexible. So can we make some energy, a fuel that we can actually transport? And this is really needed for some of these hard to abate sectors like transport, long haul transport, trucking, shipping. They need fuels that are portable. So the concept is using plasma. So plasma is highly reactive, it's highly energetic. You can do chemistry here. You can control the feedstocks. Coupling that with a catalyst is the opportunity to increase the selectivity. And there's a bunch of works already happening in this space that have demonstrated the feasibility of this idea. And here's some of our colleagues. So we're trying to form a group of us across Australia that are working in this space. This is work done by Yunjia and Emma and Jason from UNSW. So it's a collaboration between CSIRO and UNSW. And you can see here some of these concepts where using a plasma and a catalyst, so the dots are catalysts in there, and applying energy, either as solar thermal heating there or as and electrical energy in the purple to create the plasmas in both designs. Here the plasma is created in front and then it moves into the space with the catalyst. So there's lots of ways you can deploy this with the catalysts, and that's one design. Here is another, and here you can see the system in operation. So again, you have an electrode here, you create your plasma in the tube and add catalysts. So again, this is UNSW CSIRO collaboration, and the results are showing that yes, this is very possible to create fuels that we can then use using, for example, CO2. So, and there are also concepts to convert CO2 into taking CO2 and hydrogen, converting it into methanol that you can, methane that you can use as a fuel, and creating carbon products as well from that. So we can sequester ideally CO2 and create fuels from that using the electricity that we generate. So here's another concept. There's Tony, who's also in the audience, and PJ, who was with me at the IAEA. And they're working on a plasma in a liquid. So you can use it also in liquid state to do chemistry. So the plasma actually happens in the bubbles. Again, you're just taking your solar renewable energy into a transformer power supply, which you can turn off and on, and to track the variability in those solar panels. Here is a demonstration of PJ's company. This is Plasma Leap. He's working from the University of Sydney, but also with colleagues in UNSW. And this is already now having traction on-farm fertiliser, right? Creating fertilisers on-farm. So this is another exciting thing about plasma technology. This kind of, the fertilisers were made in huge factories and then shipped all over the place. Now we can actually have on-site reactors on the farm creating, with solar panels on location, creating what they need there. So we take out of the equation the carbon emissions due to transport of all of these things. And plasma lends itself to that because we don't have the need for high temperatures, and it doesn't benefit at that in the same way with scale up. So we don't need to do these things at massive scale. We can actually break them down and make these chemicals where they're needed. And here's a slide from a colleague in Adelaide. So we have skills in this area all over Australia. And he's doing something similar. He's also doing sort of fertilisers. He's using wind in this case, but same deal. It creates electricity, and plasma's perfect to plug into that. And again, on-site, this is at a winery, on-site creation of fertiliser. And that's my final slide, just to highlight that this will be economically feasible. I mean, it already is, especially if you take into account the damage that the current technologies are doing to our environment. That's not costed normally. But even in the absence of that, we are getting to something that's going to be quite viable. We just need to pull together, and we need to accelerate the development here and keep the tech in Australia and build, businesses that create and export this stuff. Thank you.